Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 6, Lesson 2 on arithmetic and geometric sequences. Okay, so in our first lesson we reviewed the idea of what a sequence was, and we also talked about how sequences could really be defined in two different ways. Either with what was called a explicit formula, in which case you're literally given a formula that says this is how you calculate the nth term of a particular sequence, or with what was called a recursive formula, which told you how each term is generated based on previous terms in the sequence. Today we're going to look at two very specialized sequences known as arithmetic and geometric. So let's jump right in and start talking about those. Here we go. Arithmetic sequences. In Algebra 1, you learned about two specific types of sequences known as arithmetic and geometric. These two types are actually special cases of linear functions, those are the arithmetic ones, and exponential functions, those are the geometric ones. And I wish we called them linear sequences and exponential sequences, but I wasn't the guy who got to come up with the terminology for these, so I apologize. It is kind of what it is. Let's talk about what an arithmetic sequence is. An arithmetic sequence is defined recursively by, given a1, so given the first term, then an equals an minus 1 plus d, or an minus 1 is equal to d. The constant d is known as the common difference of the sequence and can be positive or negative. So again, let me just make sure you get this, right? Arithmetic sequences are super easy, and they're probably ones that you've been dealing with for a very long time. The idea is you're given whatever the first term is, and then each term is equal to the previous term plus some constant that doesn't change, the common difference. Now that constant could be positive, in which case the sequence is increasing as the terms go on, or that constant could be negative, in which case the sequence is decreasing as the sequential terms move on. So let's take a look at generating some of these sequences in exercise number 1. Let me just bring it to the top of the board. For each of the following arithmetic sequences, generate the first four terms. Letter A. A1 equals negative 7, and AN equals AN minus 1 plus 5. All right, we talked in the last lesson about how to read a sequence definition that's been defined recursively. So in letter A, what we've got is the first term is negative 7, and to get any term, we simply go to the term before it and add 5. So this is pretty easy, right? When it says generate the first four terms, well, A1 is our first term, that's negative 7. A2 is going to be equal to A1 plus 5, and that's negative 7 plus 5. And that's equal to negative 2. A3 is going to be A2 plus 5, that common difference, which is going to be negative 2 plus 5, which is equal to positive 3. Let's just scoot that one over and try to get rid of all that weird formatting. And A4 is going to be A3 plus 5, and that's 3 plus 5, which is equal to 8. So really simple, right? And you certainly looked at sequences probably as early as like 3rd or 4th grade, where you had this list of numbers and you said, oh, I add 5 to go from that one to that one, and 5 to go from that one and that to that one, and 5 to go from that one to that one, so I'll just keep adding 5 in order to keep generating these sequences. All right, well, why don't you pause the video now and see if you can figure out the first four terms in both letter B and in letter C. Pause the video now and see what you can do. All right, well, letter B looks a lot like letter A. The only difference is that in letter B, right, our first term is 15, and the common difference is negative 4. We can really think of this then as each term is gotten by taking the previous term and subtracting 4 from it, right? Adding negative 4, subtracting 4, the same idea. So here we go, right? We've got B2 is equal to B1 plus negative 4. So that's going to be 15 plus negative 4, and that's going to be 11. B3 is going to be B2 plus negative 4. So that's going to be 11 plus negative 4, and that's going to be 7. And b4 is going to be b3 plus negative 4, and that's going to be 7 plus negative 4, and that's 3. All right. Now, letter C is just sort of phrased in a little bit of a different way, right? C1 is equal to 2.25. Okay, so it's a decimal, whatever. And Cn minus 1 is equal to 0.25. Now, if you really want this to look like this one and this one, what we could do is take this statement and rewrite it as Cn is equal to Cn minus 1 plus 0.25. In other words, we can just add a Cn minus 1 to both sides of this equation and rewrite it the way that it kind of looked before. But I like it looking like this a little bit because it really gets to that thing called the common difference. In other words, if I keep subtracting, two consecutive terms, I always get 0.25. Now the rest of it's pretty easy to generate, right? C2 is going to be equal to C1 plus 0.25. So that's going to be 2.25 plus 0.25, and that's going to be 2.50, or just 2.5. All right, C3 is going to be C2 plus 0.25, and I'll try to save myself a little bit of room there. That's going to be 2.75. And then C4 is going to be C3 plus 0.25, which is going to be 3.0. But I'll just keep it at 3. All right, so it's really simple. Arithmetic sequences are the simplest sequence out there, right? We take a particular number, a starting number, right? A1, B1, C1, and then we either add the same number each time to get to the next term or subtract the same number each time to get to the next term. We always sort of phrase it as being an addition problem, but if we add a negative, we're really in effect subtracting. All right, let's take a look at exercise number 2. For some number t, the first 3 terms of an arithmetic sequence are 2t, 5t minus 1, and 6t plus 2. What is the numerical value of the 4th term? Hint, first set up an equation that will solve for t. All right, so I want you to play around with this a little bit. And it's a little bit of a challenging problem to get through algebraically. It's not too terrible, all right? But I'd like you to toy with it a bit before I show you the solution. See if you can figure out what the numerical value of the 4th term is. In other words, you're going to be able to get a number like 12 or 37 or negative 10. You're going to be able to come up with an actual value for the 4th term. Pause the video now and see what you can do. All right, well, I'm just going to erase this line here so that we can see that better. Now, just for a second, I want to kind of picture what's going on here, right? I've got these, 4 terms, 2t, 5t minus 1, and 6t plus 2, and of course my 4th term, which is what I'm actually trying to figure out. Now, what I know, right, about arithmetic sequences is that I'm going to add the same thing here that I do here, that common difference, all right? But what is d? Well, d, right, is equal to 5t minus 1 minus 2t, right? The whole point is, this minus this gives me that common difference. But then again, d is also equal to 6t plus 2 minus, should be a little careful here, 5t minus 1. That's also true, right? So this minus this has got to be the same as this minus this. That's what we mean by a common difference. But this now allows me to set up an equation to solve for the variable t. Specifically, I can set those two things equal and say 6t plus 2 minus 5t minus 1 is equal to 5t minus 1 minus 2t. All right, so now let's solve this equation. Should be pretty easy. Let me get this out of the way. Whoops. Just have to distribute that subtraction. So that's going to be minus 5t plus 1. Here I'm going to combine some like terms, and I'll just get 3t minus 1. Let me continue to, let's see if we can extend the page a little bit. Combine some like terms over here. 6t minus 5t is just t. Positive 2, positive 1 is positive 3. So 3t minus 1, I think I'll just subtract a t from both sides and add a 1 to both sides. That's going to get me 4 is equal to 2t, and of course t is now equal to 2. Now that's not the answer to my problem. That is simply what t is equal to. But here's the great thing. Now I can take the value of 2 and I can actually generate the numerical values for the first 3 terms. Specifically, right, if I take 2 and I substitute it into here, right, if I take my 2 and I substitute it into here, 2 times 2 is 4. If I substitute it into here, I have 5 times, right, 2 minus 1, and that's going to be 9, right? 10 minus 1 is 9. Then if I substitute 2 into here, I'll have 6 times 2 plus 2. That's going to be 12 plus 2, which is 14. And now look, right? Do we actually have an arithmetic sequence? Well, to go from 4 to 9, I have to add 5. To go from 9 to 14, I have to add 5. So yes, I've got an arithmetic sequence because I'm adding the same amount to get to the next number, which means my fourth term is 14 plus 5, and that's 19. And that's the actual answer I'm looking for here, right? And that's very tricky. You know, what can be very tough for students is, of course, if I forget the parentheses around the 5t minus 1 here, right, thus never distributing that subtraction, I'll get a value for t. But it will actually give me a sequence here that is not an arithmetic sequence, okay? And it would be easy to see that. Whatever that sequence ended up being, it wouldn't be arithmetic, and it would be like, oh, I add 3 here, but I add 5 here. You know, that's not arithmetic anymore. All right, let's keep going. Let's talk about explicit formulas for arithmetic sequences. Now, we talked about explicit formulas in the last lesson. It's important to be able to create an explicit formula for the terms of an arithmetic sequence. You saw this formula back in Algebra 1, but we will quickly review its development in the next exercise. Let's take a look at exercise number 3. An arithmetic sequence is given by a1 equals 12 and an equals an minus 1 plus 5. Answer the following questions. Letter A. How many times would the common difference need to be added to a1 to produce a4? Illustrate. Well, let's talk about this together because everything you need to understand the explicit formula for an arithmetic sequence is going to happen right now, right here in letter A. Let's take a look at it, right? So I'm going to just kind of do the same thing I did in the last problem, right? I've got 12. And I'm going to add 5 to it, and I'm going to get 17. And then I'm going to add 5 to it, and I'm going to get 22, and I'm going to add 5 to it, and I'm going to get 27. Okay? Now notice, right, this is my A1, this is my A2, this is my A3, and this is my A4. And although it would be very tempting to say, well, we're going to have to add 5 4 times to go from A1 to A4, that's not true, right? We actually only add 5 3 times. Now, if for some reason we arbitrarily said the first element of a given sequence was a sub 0 instead of a sub 1, well, then we would have to add 5 4 times to get to a4. But that's just not what we do here, all right? So we have to add it 3 times. And that's because we start at A1, right? And then we add it once to get to A2, twice to get to A3, and 3 times to get to A4. Okay, now let's take a look at letter B. What is the value of A sub 50? Think about part A. In other words, I want you to come up with the 50th term, and what I certainly don't want you to do is sit there and go plus 5, plus 5, plus 5, plus 5, plus 5. I don't want you to do that. So pause the video now and see if you can figure out how to generate the 50th term of the sequence and then figure out its value. Well, to get to the 50th term, unlike the 4th term, we're going to have to add that 5 49 times, right? 49 times. And I'm going to write that down. Add 5 49 times, right? Now again, we could add the 5 49 times to 12. It would just take us a while on the calculator, but it's a lot easier to just say the following. A sub 50 is going to be our starting value, 12, plus 49 of those 5s. Right? That's the whole point of multiplication, is to be able to like circumvent adding a number, the same number again and again and again, right? And of course, this is very easy to put in our calculator. And once we do that, we end up having 257. All right. No reason to break out our calculator to do that. All right. So simple, right? And this really then can lead us to developing a general formula, a general explicit formula for an arithmetic sequence. Let's take a look at letter C. If a general arithmetic sequence starts with A1 and has a common difference of D, develop a formula for the nth term of the sequence A sub n. All right, well, why don't you take a shot at it? See what you can do. Pause the video now and see if you can come up with this general formula. Let's do it exactly the way we just did it, right? So A sub n, right, is going to be generated by taking our first term and adding to it n minus 1 of those common differences, right? So to get to the 50th term, we added 49 of those d's. To get to the 4th term, we added 3 of those d's, and there it is. There's our explicit formula, right? A sub n is equal to our first term plus 1 less than the number of terms times the common difference. And now let's generate an actual explicit formula in letter D. Use C to determine an explicit formula for A sub n if A sub 1 equals 12 and A sub n equals A sub n minus 1 plus 5. All right, why don't you go ahead and do that? Well, let's do it. Simple, right? A sub n now is going to be 12 plus n minus 1 times 5. Now, I really like the formula just written like that because it really gets at it, right? That's it, man. I'm starting with 12, and then whatever my n is, I'm taking 1 away from it, right? And I'm adding that many of the common differences in. I really like that. But you can imagine a scenario, right? Probably a multiple choice problem, something like that, where this is not one of the choices, and what they've done is they've sort of simplified this, right? So one can simplify this formula, and again, that's a perfectly good answer. I want to be very clear about that. By distributing that 5 through the parentheses, right? Just multiplying that thing through, and then combining those two constants and getting something that looks like this, right? So both of those are perfectly good. All right. The big difference is that in one of them, it's kind of written in this way that you can really see the process. That's my first term plus 1 less than the number of terms times the common difference. This one, honestly, I don't really love. I don't love it, but you'll often see that in a multiple choice scenario because, well, quite frankly, it's a shorter sort of looking answer than this one. All right, let's keep working with this recursive versus explicit representation of an arithmetic sequence. Moving between the explicit and recursive forms. It's important to be able to move between the explicit and recursive form of an arithmetic sequence. In fact, it's a fluency expectation at this level that you can go kind of fluently between the two. So let's take a look at that process in exercise number 4. For each scenario below, an arithmetic sequence is given in either recursive or explicit form. Translate into the other form of the sequence. All right, great. So let's take a look at letter A. A sub n equals 8 plus n minus 1 times 14. All right, so this is what's known as the explicit form. In other words, if I asked you what the 100th term was, you could just substitute 100 in for n and you could calculate it out, right? You wouldn't have to, do it based on the previous element, right? But that's the point, right? This is the explicit formula. Let's actually write that down. Let me be very clear. That's the explicit. So what we want is we want now the recursive formula. All right, and in a recursive formula, you always want to do two things. You always want to tell what the beginning value or values is, in this case just the beginning value, and then the rule that tells us how to calculate the next value based on previous values. So for the recursive definition, right, what I know is that my first value is most certainly 8, right? And if you're not sure about that, if you're not sure if a1 is equal to 8, take 1 for n and substitute it in. And if you put n equals 1 in here, this would be 0 times 14, because we're not adding that 14 at all. And that would mean we would be left with a sub 1 equals 8. Now, what are we adding each time? Well, we're adding 14, right? Again and again and again and again. So that means that an is equal to an minus 1 plus 14. And that is my recursive definition based on that explicit definition. All right. Why don't you go ahead and play around with B and C? Be careful on C. It's a little bit tricky. Pause the video now and see what you can do. All right, well, letter B is literally going in the opposite direction of letter A. In other words, in letter B, what we've been given is we've been given the recursive definition, and we want the explicit. All right. So here, it's pretty easy, right? The explicit definition, right? We know that Bn will have to be equal to B sub 1 plus n minus 1 times D. Now we just need to plug in our numbers, right? B1 is 11, n minus 1 just stays as n minus 1, and then our D is negative 3. And that would be a completely fine way to leave it. There is nothing wrong with leaving it that way. It's definitely explicit. If I gave you, a question like, what is the 200th term? You could put in 11 plus 200 minus 1 times negative 3, and you could generate the 200th term. If you really wanted to clean it up, you could distribute the negative 3 through, and eventually what it would look like, if you, quote, cleaned this up, is it would look like B sub n equals 11 minus 3n plus 3, and B sub n would be negative 3n plus 14, right? So this would be good, or this would be good, either one of them. And I know what many of you are thinking right now if you're a student, well, if they're both good, then I'm stopping here. I'm not going to keep going, right? And that's fine. Again, it would kind of depend on the context of the problem. Is it free response? Is it multiple choice, right? What are we looking to do? Now, letter C is a little bit trickier. One thing that I think that we can definitely say for certain is that this is explicit, right? This is definitely an explicit formula. And therefore, what we want is we want the recursive definition. Now, this could be a problem because it would be very easy to be like, oh, maybe C1 is 5 and the common difference is 3 because I'm adding it on, Or maybe C1 is equal to 3 and the common difference is 5, right? Which way is it? All right, well, if you're not sure, one thing that is good to do is to generate the first few values of this particular sequence. So let's take a look at that for a second. Let's figure out what C1, C2, etc. Right? C1 would be 5 times 1 plus 3, which is 5 plus 3, and that's 8. C2 would be 5 times 2 plus 3, and that's 10 plus 3, which is 13. Let me get that out of there. Right? C3 would be 5 times 3 plus 3, which is going to be 15 plus 3, and that's 18. And I think that that's enough, right? And what I can definitely see here, number one, is that C1, my first term, which I need in every recursive definition, C1 is neither 5 nor 3. It's equal to 8, right? So you have to be very, very careful in that sense of just like sort of grabbing a number. So definitely C1 is equal to 8, but then that common difference, right? What did I add each time? Well, that's plus 5, and that's plus 5. In other words, if you will, the slope, right, of this line is that common difference, right? We're getting to add an extra 5 for each value that n goes up. And we saw that time and time again, right? In this particular problem, right, the 14 ends up being the common difference. Here, right, when I worked it all out, that like number multiplying the n, the -3, that was the common difference. Here the common difference is 5, so now let's define it recursively. We can do our recursive definition, and that's C1 is equal to 8, and Cn is equal to Cn minus 1 plus 5. And there's our recursive definition. So be careful. You know, if you ever are trying to move from explicit to recursive, right, generate some terms. Generate, you know, the first term, second term, third term, if you need to, fourth term, look at the pattern and make it work. All right, let's keep going. Now let's talk about geometric sequences. Another type of sequence that uses multiplication instead of addition to generate terms is known as geometric. All right, let's take a look at geometric sequences, which I would really prefer them to call exponential. Let's take a look. A geometric sequence is defined recursively by, given a1, then an is equal to an minus 1 times r, or an divided by an minus 1 is equal to r. The constant r is known as the common ratio. All right, so right, in arithmetic sequences, what we were doing is we were always starting with some number, and then to generate any number, to generate any term, we were taking the previous term and adding, you know, or subtracting a particular constant. For a geometric sequence, instead of adding, we're going to multiply each previous term to get the next term. And it's called the common ratio because anytime we divide two consecutive terms, we will always get that number r, that constant ratio. So let's take a look at generating some geometric sequences. Exercise number 5. Generate the next two terms of the geometric sequences given below. Letter A, a1 equals 4 and r is equal to 2. Again, very, very similar to an arithmetic sequence. The big difference is, right, if I want a2, that's going to be a1 times r. That's going to be 4 times 2, and that means a2 is going to be 8. Right? a3 is going to be a2 times r, and that's going to be 8 times 2, and that means a3 is going to be 16. And maybe we'll even make that look like a 3, or we'll try. All right. That's the whole idea, right? It's no more difficult than an arithmetic sequence. The difference is instead of adding to get to the next term, you're multiplying to get to the next term. Why don't you go ahead now and pause the video and see if you can do letters B and C. All right, well, maybe B gets a little bit more ugly because we're multiplying by 1/3, but I still tried to make the numbers sort of turn out nicely, right? B2 is going to be B1 times 1/3. That's 9 times 1/3, and that gives me 3. And B3 is going to be B2 times 1/3, and that's going to be 3 times 1/3, and that means B3 is going to be equal to 1. All right, and finally, letter C. Very similar to letter C when we did the arithmetic sequences, I've got Tn divided by Tn minus 1 is equal to -4. Now again, if this is bothering you, making it look this way where they literally give me that, you could rearrange this into Tn is equal to Tn minus 1 times -4. You could just rewrite it that way. Right? Now it's very clear. Every term is going to be gotten by taking the previous term and multiplying it by -4. So T2 is going to be T1 times -4. That's going to be -2 times -4. So T2 is going to be equal to +8. T3 is going to be equal to T2 times -4. And that's equal to 8 times -4. So T3 is going to be -32. All right, simple as that, right? No big deal here. Let's keep going. An explicit formula for geometric sequences. Like arithmetic sequences, a geometric sequence can also have an explicit formula. And it's going to be very similar to what we did before. Let's take a look at exercise number 6. Consider a1 equals 2 and an equals an minus 1 times 3. Letter A, generate the value of a sub 4. Awesome. Well, why don't you go ahead and figure out what a sub 4 is equal to? All right, well, I'm gonna kind of do this problem and then we'll immediately jump to B, right? So what we know is that each term is the previous term times 3. So a2 is a1 times 3, so that's going to be 2 times 3, which is 6. a3 is going to be a2 times 3, and that's going to be 6 times 3, which is 18. And a4 is going to be a3 times 3, and that's going to be 18 times 3, and that's 54. All right. Had to look at that a little bit. I normally don't do 18 times 3 in my head very often, but I'm pretty sure it's 54. All right, let's take a look at letter B. How many times did you need to multiply 2 by 3 in order to find a sub 4? Well, this is pretty easy, right? We multiplied it by 3 once, twice, 3 times. 1, 2, 3. 3 times. And again, just like the arithmetic sequence, notice that the number of times we had to multiply by that constant ratio was 1 less than the term number. And that makes sense because we start with a1. Then we multiply once to get to a2, again to get to a3, and 3 times to get to a4. That being said, let's now figure out in letter C the value of a sub 10. And I would definitely suggest using your calculator for that one. Now, I could take 2 and multiply it by 3 9 times, right? Because it's a sub 10. But to be very specific, right? If I want a10 and I'm starting with 2 and I'm multiplying it by 3, I'm going to multiply it by 3 9 times. So I'm doing 2 times 3 to the 9th. And you can probably now see why I would much prefer to call this an exponential sequence rather than a geometric sequence, right? This looks almost exactly like an exponential function, right? A times b raised to the x kind of business. And of course for this, I definitely don't want to do that in my head, but whatever, I can definitely do 2 times 3 raised to the 9th on my calculator. Simple, right? Geometric sequences, especially when the ratio is greater than 1, tend to get very big very quickly. Arithmetic sequences can kind of limp along and give you a value, but boy, geometric sequences get big and fast. So we're talking about 39,366 as our 10th term. All right. And just like with our arithmetic sequence, let's take a look at letter D. Write a formula for the nth term of a geometric sequence a sub n based on the first term, a1, r, and n. Okay, go ahead and try to come up with this formula. All right, well, here we go. Just like before, right, an, we're going to get by taking our first term, multiplying it by that constant ratio raised to the n minus 1. And that's it, right? We simply find our nth term by taking our first term and multiplying it by that constant ratio 1 less time than the number of terms that we're looking for. All right, let's do one more problem on this. Exercise number 7. On day 1, 5 people hear a rumor. Each day, the number of people who have heard the rumor doubles. Let a sub n be the sequence giving the number of people who have heard the rumor for a given day n. Letter A, give a definition of the sequence in recursive form, and letter B, give a definition of the sequence in explicit form. All right, pause the video now and see if you can do both A and B. All right, well, A is pretty easy, right? A sequence in recursive form, well, on the first day, right, A1, 5 people have heard the rumor, right? Now, every day, the number of people who have heard the rumor simply doubles from the day before. And therefore, that is our recursive definition for this sequence. Now, the explicit formula, on the other hand, right, one that I could literally use to calculate how many people had heard the rumor, let's say on the 100th day, without having to generate all the previous values, well, that starts with my original number, which is 5, and then I'm going to multiply that by my constant ratio raised to the n minus 1 power. And that's it. Right? There is my explicit formula. And again, the huge advantage of the explicit formula is that you can take it, and if I said how many people heard this rumor on the 35th day, you could take this and plug 35 there in for n. By the way, it would be an enormous number, probably more people than are on Earth, but you know, we'll leave that for another day, so to speak. All right, let's summarize. So we began this unit talking generally about sequences, how they're defined both explicitly, recursively, what they are, etc. And then today we drilled down a little bit deeper into 2 very specific types of sequences, arithmetic and geometric. Arithmetic sequences are ones where we add or subtract the same number each time to get to the next element or, the next member of that sequence. Or geometric sequences, right, are very, very similar, and they're ones in which we start with a particular element, and to get to each next element, we multiply by the same number. In both cases, what we definitely want to be able to do is define these sequences recursively, that should be the easy part, but also explicitly with formulas. And those explicit formulas can be a little bit tricky because they always are referring to n minus 1. Right? One less time that we add that common difference, or one less time that we multiply by that constant ratio. We're going to definitely get a lot more work with both arithmetic and geometric sequences as this unit progresses. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.